Sure, thank you.
So, let me welcome everybody to this issue of Gauge Theory Virtual. We've got Aleksander speaking about pseudo-holomorphic curves and symplectic 6 manifolds. I will let him take it away.
Thank you, and thank you for the invitation. So today's talk is inspired by some questions in symplectic geometry, but the methods I will use and ideas come from geometric measure theory, and are also inspired by some ideas in gauge theory. So towards the end of the talk, I will explain the connection to gauge theory. And everything I'm going to talk about today is joint work with Tomasz Walpuski. I will also state one recent result, which is joint with Eleni Ionel and Tomasz Walpuski. So let me begin with an old problem from algebraic geometry. Given a complex projective manifold X, count holomorphic curves which satisfy certain conditions. For example, you fix genus and the degree or equivalent in a homology class, and maybe specify additional constraints that your curves pass through a collection of points or a collection of submanifolds. And this is something that was studied for a long time in the 19th century, going back to people like Schubert and the Italian school of algebraic geometry. And of course, there are many beautiful results, such as, there are 27 lines containing a cubic surface and so on. So this is the starting point. And to give a little bit more detail, in general, given G, integer, a non-negative integer, and a homology class A, you consider the moduli space of curves of genus G representing this given homology class. This moduli space has an expected or virtual dimension given by this formula. And if this formula gives you 0, then it is reasonable to consider the problem of simply counting these curves, because you expect that these curves don't come in families and you can simply count them. And what is important in this formula, that something very interesting happens when the dimension of X is 3, and when the first class of X is 0, then no matter what genus or homology class you choose, the virtual dimension is 0. So this is the case of Calabi-Yau threefolds. So this is very nice because all moduli spaces have virtual dimension 0. Of course, that doesn't mean that the moduli space of curves is actually a 0-dimensional manifold. And this is a big problem in this theory. In what sense do you count the curves if the moduli space is actually not of expected dimension? And one way to solve this problem is through Gromov-Witten theory. So let me zoom out. So more generally, you can consider X being a symplectic manifold, and you consider almost complex structures which are compatible with the symplectic form, namely that this tensor given by this formula defines a Riemannian metric. So in particular, J is orthogonal with respect to the Riemannian metric. And instead of studying curves, you can study J-holomorphic maps. So these are smooth maps from Riemann surfaces, such that their derivative is J-linear. So sigma is a Riemann surfaces, and small j is a complex structure on sigma. And you require that this Riemann surfaces has genus G, and that the map represents a given homology class A. And modulo parametrizations, these maps form the moduli space of J-holomorphic maps. In particular, such maps are harmonic. And the main one of the main results of Gromov-Witten theory is that there is a natural compactification of this moduli space called the moduli space of stable maps, which I denote by MGA bar. And this moduli space consists also of maps, but maps from Riemann surfaces which are possibly singular, and we allow we allow the singularities to be nodal, and we moreover add the stability condition for maps, and that's why they're called stable maps. And Gromov's compactness theorem says that this moduli space of stable maps is compact, even though the original moduli space of smooth maps is not, of maps from smooth Riemann surfaces is not necessarily compact. Now, if the virtual dimension is 0, so for example, in this Calabi-Yau case, you can use this moduli space. You can construct a virtual fundamental class on this moduli space and integrate it against the cohomology class 1 that defines a Gromov-Witten invariant. And this Gromov-Witten invariant is a rational number, essentially because this moduli space has orbifold singularities, orbifold points. So this is one way in which you can make this problem of counting pseudo-holomorphic curves precise. You embed your space of curves into the space of maps, then you compactify the space of maps, and you use the virtual fundamental class to define the Gromov-Witten invariant. And in the end, you show that this invariant does not depend on the choice of an almost complex structure as long as it's compatible with a symplectic form. But from a geometric point of view, this is not so satisfactory because this moduli space is gigantic and contains a lot of maps which are not embedding. So it's not that every point of the moduli space corresponds to an embedded holomorphic curve or pseudo-holomorphic curve. So one example which you already see without the compactification, just in the moduli space of maps, that you can have a pseudo-holomorphic map and a branched multiple cover over Riemann surface, and the composition is again pseudo-holomorphic and has the same image as the original map. If you consider the compactification, it becomes even worse because you have to add maps which are constant on some components. So these are called ghost components. So for example, you could have a nice embedded genus 0, a nice pseudo-holomorphic sphere, which is embedded, everything is fine. But then you can just add, a higher genus surface. So you consider this nodal Riemann surface with two components, and you take the map which is identity on the sphere component and maps everything else to a point. And such a map will represent the same homology class. It will have a different genus, but it's a perfectly fine element of the moduli space. And of course, all of these because in the end, I'm integrating the virtual field contributions in general. So we get an invariant, but there is a price to pay. That in some sense, you get an invariant, but it's not obvious what exactly it counts. So a question you can ask, are there symplectic invariants which count embedded pseudo-holomorphic curves, possibly with some weights, that have more geometric meaning than the Gromov-Witten invariants? So, of course, the simplest case is one of these examples I mentioned at the beginning of the talk. In algebraic geometry, we actually have a lot of interesting examples in which we're using methods of algebraic geometry. We can simply count embedded curves. But more systematically, in dimension 4, Taubes defined an invariant for any symplectic form manifold by counting embedded pseudo-holomorphic curves with certain weights. So the individual numbers of curves are not invariants, but if you equip them with some weights, that becomes an invariant. So that's something like that exists in higher dimensions. So, I mean, this is not a theorem, but somehow my expectation is that for a general symplectic manifold, you shouldn't expect such an invariant to exist. So in general, there is no reason for the count of embedded J-holomorphic curves to be independent of J. Even worse, if you fix J, it is not obvious that you will have finitely many curves. Because even if you only consider these embedded curves, of course, the point of Gromov-Witten theory is that embedded curves interact with these other elements of the moduli space. So for example, they can embedded curves can degenerate to multiple covers, or embedded curves can, from the point of view of pseudo-holomorphic maps, can degenerate to maps with constant components. So if you want to define such an invariant, you should have some reason, for example, given by index theory or intersection theory, some reason why you would expect this invariant to exist. Again, this is not a theorem, it's just some kind of expectation that you wouldn't be able to do it in general. Now, this case of Calabi-Yau threefold is particularly nice because the index formula tells us that all moduli spaces are zero-dimensional. So that's a very special case. And indeed, for Calabi-Yau threefolds, we know that there exist various invariants defined using algebraic geometry, which in some sense count embedded objects rather than maps. So these objects could be, for example, one-dimensional subschemes, as it is the case in Donaldson-Thomas theory, or certain sheaves with sections, as in the case of Pandaren-Pandey-Thomas theory. So subschemes are not exactly curves, but in some sense, they are embedded objects and not parametrized objects. So that's the main difference with Gromov-Witten theory. And the nice thing is that these invariants in algebraic geometry are actually integers. So even though you define them using virtual fundamental classes, in the end you get an integer rather than a rational number. So you can think maybe this integer has a symplectic definition as a count of some objects, maybe curves with weights. So the motivating question for this talk is, can we define such invariants for Calabi-Yau, for these Calabi-Yau threefolds, or more generally symplectic six manifolds? Or can we find a symplectic definition of these Donaldson-Thomas and Pandaren-Pandey-Thomas invariants? And so towards the end of the talk, I will explain some ideas how to define a symplectic version of the Pandaren-Pandey-Thomas invariants. But for now, I want to state a theorem which says that in some very special cases, simply the naive count of curves without any weights is a symplectic invariant. So this is the following theorem with Tomasz Walpuski. So let X be a compact symplectic manifold whose real dimension is 6 and with vanishing first-term class. So this is a symplectic analog of a Calabi-Yau threefold. Now, for a generic almost complex structure, which is compatible with a symplectic form, there are finitely many embedded J-holomorphic curves in every homology class. So since there are finitely many curves, given a genus and a homology class, you can define a signed count of these curves, which I call here NGA. And there is a natural way of equipping these curves with signs using index theory. And the second part of the theorem says that if A is a primitive class, then the signed count of these curves is independent of J and therefore is a symplectic invariant of X. And what I mean by primitive, I mean that A is not K times B, where B is also an integral class and K is an integer. So there's an observation here. In the theorem says there are finitely many embedded curves. It doesn't say curves of a given genus. So that means that no matter what genus, there will be finitely many curves. So in particular, the signed count of curves for large genus is 0. Because if there are finitely many curves, there is a maximal genus in the set of curves. And another remark I want to say is that there is a generalization of this theorem to arbitrary 6-dimensional manifolds. So this condition, in some sense, this case when the first-term class is 0 is the most important case. Because in general, you can split all homology classes into the ones that pair to 0 with the first-term class, positive number, and a negative number. The positive case and negative case are less interesting. So are there any questions about the statement of the theorem?
Is it G is equal to 0 makes sense in this theorem?
Yes, G can be any natural number or 0.
Mm-hmm. So, yeah.
So of course the statement here that A is a primitive is a very restrictive. It's a very restrictive condition, and later I will talk about some ideas what to do when A is not a primitive class. That's a more interesting case. So the proof of this theorem is inspired by Taub's work on symplectic form manifolds and uses some new result from geometric measure theory. So I want to outline the main ideas and work of other people involved in the proof. So first you choose a generic J so that the moduli spaces of simple maps, the moduli spaces of curves are all discrete. So this you can always do. You can always, this is just a transversality result for J-holomorphic maps. So when I write moduli space of curves, I don't mean the compactified moduli space. I just mean the actual maps from smooth Riemann surfaces. And because we're in dimension 6, and these are maps from 2 manifolds, we can also arrange that all of these pseudo-holomorphic maps will be embeddings that will have pairwise disjoint images. So any 2 different pseudo-holomorphic maps will have disjoint images. So let's now focus on the first part of the theorem, which said that for a generic J there are finitely many curves. So assume by contradiction that there is an infinite sequence of curves in the same homology class. And again, I do not care about the genus of these curves. So now for every curve, I can define the current, which is given just by integration of 2 forms over the curve. And the mass of this current, because these curves are J-holomorphic, the energy identity for J-holomorphic curves tells you that the mass of this current is a topological quantity, is the pairing of the cohomology class of the symplectic form with the homology class of the curve, which here is fixed. So that means that in my sequence of curves, all of them have the same mass. All of these currents have the same mass. So if you have such a sequence of currents, the Federer-Fleming compactness theorem in geometric measure theory tells you that you can pass to a sequence which converges weakly to a current which is integer rectifiable. So in general, you get the limit, but it's some sort of current, so it can be very singular. But because the original sequence was of J-holomorphic curves, the limiting current will be also J-holomorphic, meaning that at almost every point it has a tangent space, and the tangent space, the tangent plane, is invariant under J. So now there is this work of the Lelis, Padauer, and Spolar on the regularity of calibrated currents. Actually, I should mention here that, that for this particular step, we could use earlier work of Vivier and Tian. So earlier work. But I'm using this paper of the Lelis, Padauer, and Spolar because it will be important for the next step. The point is that the limiting current, there is a regularity theorem for the limiting current. And essentially what will happen is that the limiting current will be a combination with integer coefficients of Dirac deltas supported on pseudo-holomorphic curves. So it's as good as you want it to be. But now, because the support of this current is connected, and by the first step for a generic J, all pseudo-holomorphic curves are pairwise disjoint, that means that there is only one pseudo-holomorphic curve. So in fact, in the sum, there is only one, n is equal to 1. So that means that the limit of my original sequence is simply m, some integer, times a single curve C, which again, by the first step is embedded. So once we get this limit, we can use an idea of taubes. So I have this limiting curve C, and I have a sequence which converges to that, so which collapses to C. So what I can do, I can look at the tubular neighborhood of that curve and start rescaling in the normal direction. So the original sequence was collapsing to C, but now I can always rescale so that the sequence is at the Hausdorff distance 1 from the limiting curve. So maybe this is not a good picture. So if this is C, I have some Cn, and I consider Cn, oops, maybe Cn twiddle, which is rescaled so that the Hausdorff distance is 1. And now the point is that this rescaled sequence will also have bounded mass. They will be no longer holomorphic with respect to the original almost complex structure, but with respect to some rescaled almost complex structure. But the point is that the sequence of these rescaled almost complex structures converges to another almost complex structure. So since the sequence has a bounded mass, I can use the same trick that I used before. So I can say, after passing to a limit, after passing the subsequence, there is a limit of this rescaled sequence. The limit will be some sort of pseudo-holomorphic curve with respect to a different pseudo-holomorphic current with respect to a different almost complex structure. And by the same regularity theorem, it will be of this form. So the point is that in the limit, I get some other combination of curves, which are called C twiddle. So for the sake of the argument, let's just assume that after rescaling, I get a single curve C twiddle. And that curve C twiddle is different than C because the Hausdorff distance of the support of this the Hausdorff distance of this curve to that curve is 1, because that was the Hausdorff distance of the rescaled sequence. So now, so the picture is this, that after rescaling, I found some other curve C twiddle. And now the point is, that maybe this curve looks like this. So the point is that over every point of C, I can look how many, this is in the normal bundle, so I can look how many points are there above a given point in C, and that defines me a multi-valued section of the normal bundle, because over every point of C, I have some number of points in C twiddle. And some computation shows you that this section of this multi-value section of the normal bundle is not a random section, it satisfies the PDE. So in some sense, it's a pseudo-holomorphic section. Now, the pseudo-holomorphic section can be understood as follows, that over C, I have the normal bundle, and I can twist this normal bundle by some flat vector bundle, so by a local system. And this multi-valued pseudo-holomorphic section can be understood as a section of this normal bundle twisted by a local system, which satisfies some Cauchy-Riemann type equation. And now the point is, so this is twisted by E. Now the point is that the index of this operator, and this is again something very special to Calabi-Yau manifolds, that this index will be always negative. Sorry, non-negative, non-positive. So that means that for a generic J, if everything is generic, I don't expect this operator to have any kernel. So I don't expect this section to exist. And this is exactly the content of the superrigidity theorem, which was recently proved by Wendell, that for a generic J, I can always achieve equivariant transversality for such operators, and I can always guarantee that there are no solutions to this equation. So that's a contradiction, because I have just found such a solution. And I know that my solution is non-zero because my section, essentially because C twiddle was not equal to C, that my section must be non-zero. So this contradiction shows that there couldn't be an infinite sequence of curves in the same homology class. So this proves that there are finitely many curves for a generic J. And maybe I'm stressing this too much, but the point is that the genus of the curves does not matter in this argument because we're not using Gromov compactness for pseudo-holomorphic maps. So if you're a symplectic geometer, maybe you're used to thinking about curves of a given genus because that's what Gromov-Witten theory deals with. But that's not what we're using here. We're using compactness for pseudo-holomorphic currents. So if you have finitely many curves, of course, you can you can equip them with some signs. There's a standard way of doing that, and you can count them. But the point is that in general, this count will depend on your almost complex structure J. So let me explain why the count is in order to see why the count is independent if A is primitive, let's see how it can change when I vary J. So the proof of the above theorem fails when J varies in a family because these multi-valued pseudo-holomorphic sections can appear. So I'll scroll to the previous slide. So now if you try to do this proof, but now you assume that the curves are pseudo-holomorphic with respect to different J's. So you allow J to vary. Everything is exactly the same until you reach this last step. So in the last step, we use the fact that the index of this operator was non-positive. So in particular, if the index is 0, then even though for a generic J, you will not have any solution, but for a J along a generic one-parameter family, you will encounter special J's for which this operator actually has a kernel. So an element of that kernel will correspond to one of these multi-valued sections of the normal bundle. And by reversing the entire argument from a multi-valued section, you can produce J-homomorphic curves which collapse, J-homomorphic embeddings which collapse to a multiple cover. So let me explain this here again. So these multi-value sections are related to the following phenomenon. So suppose that your homology class is not primitive, so it's M times B for some other homology class. What can happen is that the sequence of embedded curves in class A can collapse to an M-fold branch cover of a curve in homology class B. And this is a cartoon of how this can happen. Right, so here these parabolas collapse to double line. So then the M-valued section of the normal bundle remembers the infinitesimal direction of this collapse. So before the collapse, I could look at the normal bundle of this limiting curve, and I would have 2 points over each point of the limiting curve. That gives me a two-valued section of the normal bundle. And because of this collapse, so maybe I didn't say it, but if this happens, of course, then the number of curves representing this homology class, number of embedded curves changes, because once this curve collapses, it no longer exists. So the upshot of this discussion is that the naive count of curves NGA, even though you can define it for a generic J, but for a general homology class, it will depend on J, because some embeddings can degenerate to multiple covers. But now if A is primitive, this doesn't happen, because simply for topological reasons. Because if this happens, then A has to be M times B, where B is the homology class of the curve to which we collapsed. So actually, there's some technical point that even though A is primitive, it could still technically happen that you have a sequence of curves of higher genus, and maybe some of the genus collapses. So how to draw it? So maybe something like this could happen. No, I only got it wrong, sorry. So the region with genus becomes smaller and smaller until it disappears. So you started with something with higher genus, and you got something with lower genus. So you still have to rule out that this happens if you want to really show that each of these numbers NGA is invariant. But this you can do by essentially what you have to prove, that when this happens, this limiting curve here has to have a cusp or some sort of singularity. But this is again a non-generic phenomenon, because for generic J, all curves are embedded. So something like that, following ideas of Ionel and Zinger, can be proved by studying the gluing problem for pseudo-holomorphic maps. So this is related to these ghost maps that I mentioned earlier. In any case, the upshot is that when A is primitive, this number NGA is independent of J. And I mean, this is some sort of technical part, but the main reason is really that it is topological, that I cannot have a collapse to multiple cover. So are there any questions about this part of the proof?
I have a question. So when you use geometry measure theory to get a limit curve, like, is that curve a really embedded curve, or what kind of regularity that curve have?
So in general, the regularity theorem does not tell you that it's embedded. It could have isolated singularities. Essentially, the singularities of a J-holomorphic map. But so in the first part of the argument, we got some limit. But now this limit is a J-holomorphic with respect to the original J, which we assume to be generic. And then we just know that for generic J, all J-holomorphic curves are embedded. So this one actually will be embedded. And that's a very important part of the argument, because we want to take its normal bundle. So for that, you need it to be smooth. In the second part of the argument, when we do this rescaling and we get C twiddle, we actually don't know that it's embedded, because it's not J-holomorphic with respect to the original J, because once you start rescaling, you change J. So it's J-holomorphic with respect to some other J. But for that one, we don't actually need it to be, smooth. We just need it to be an image of a section of the normal bundle. So this section, a multi-valued image. So we don't actually need it to be smooth. I guess if it's an image of a section of a genuine section of the normal bundle, it's going to be smooth because it's going to be a graph. But if it's a multi-valued graph, we don't necessarily know it's smooth.
Okay, thank you. Yes.
I had a question about the bundle N. What is that?
Yes.
Is that a flat bundle over C? Is that what you said?
No, sorry. So N is a normal bundle.
So the bundle E, I should say, the bundle E.
Right. E is a flat bundle.
Right. But does that work at the branch points as well?
Yes. So the point is that anytime you have a multi-valued, let's see. So if you have a, sorry, C twiddle, which is the branch cover of C, you can, let's see. So this guy has a normal bundle. And this guy has, let me clear the picture a little bit. So this guy has a pullback bundle. And now sections of that, you're right. So sections of that will correspond to sections of N twisted by a, sections of this pullback will correspond to sections of N twisted by a flat bundle, but you have to allow orbifold bundles. So you encode the, exactly, I forgot to say it. So you encode the, right, the singularities of this branch cover in orbifold structure on C, and then E is an orbifold local system.
I see. Right. Thank you.
You can also remove these points and then work on a non-compact manifold. So that's something that Wendell does by looking at these operators of genuine local system, but over point, what's the word? Punctured Riemann surfaces.
What's the significance of E being flat in the proof?
Because now you look at this as such an operator. Now, if you look at this operator, DJ, on this bundle, it always has some symmetry. So you cannot naively expect that it will always have. For example, you cannot expect that the dimension of the kernel will be always given by the index formula. Because you have to work in some sort of equivariant. It's an operator with an action of a finite group. I think that's what I should say. And that's because this.
I see. Thank you.
So this result is related to the Gopakumar-Vafa invariance of symplectic sixth manifold. So there is this work of Gopakumar-Vafa inspired by M theory. So Gopakumar-Vafa predicted that if you look at all of the Gromov-Witten invariants of a symplectic sixth manifold, you put them in some generating function, that this generating function can be written in a different way by some other power series with integer coefficients. So there's some universal formula which describes the generating function of all Gromov-Witten invariants of a symplectic sixth manifold in terms of some formal series with integer coefficients. And in physics, so the physics interpretation is that these BPS numbers, these integers, count so-called BPS states supported on J-holomorphic curves. And so far, there is no mathematical definition of this BPS invariant because nobody knows how to make mathematical sense of these BPS states. There are some approaches in algebraic geometry using sheaf theory. So now you can, instead of trying to define these numbers BPS, you can do the opposite. So you can say, well, take this formula that Gopakumar-Vafa predict, and now define these numbers, because this is just a formula of powers of power series. Now define these numbers BPS in terms of the Gromov-Witten invariance using this formula. And the formula is explicit. I could write it down, but it's not very enlightening. It's just a long formula. So once you define these numbers BPS in terms of the formula, it's not at all obvious that they are rational, because Gromov-Witten invariants are rational, and the coefficients in the formula are also rational numbers. So you get some rational combination of rational numbers that is well defined, and it is an invariant because Gromov-Witten invariants are, but it's not at all obvious that these numbers are integers. So then you can pose the following conjecture, that if you define these BPS numbers in terms of the Gromov-Witten numbers using this universal formula, then that these numbers are integers. And there's a second part, that these numbers actually are 0 when G is large. So for every X and every A, these numbers are non-zero only for finding many values of G. So this is called the integrality part. And this is the finiteness part of the conjecture. So the integrality part was proved by Ion and Parker, but their proof didn't prove the finiteness part essentially because they had to use Gromov compactness, which assumes that, which only deals with pseudo-holomorphic curves of a given genus. So now these BPS numbers are related to these naive counts of curves if A is a primitive class. So Zinger showed that if A is a primitive class, the BPS numbers, which are given by this Gopakumar-Vafa formula, are simply the signed count of curves, which I denoted NGA. So this is then what I call the naive count. So since our finiteness theorem shows that these numbers are 0 for large genus, and this is for a trivial reason that there are finitely many curves no matter what genus. So that means that there is a maximal genus, and for all G above that genus, these numbers are 0 by definition. So this theorem I stated earlier shows that this finiteness part of the Gopakumar-Vafa conjecture holds when A is a primitive class. Now for A non-primitive, it is no longer true that the BPS number is the naive count. If that were the case, that would be very bad, because I just said that this number, naive count, should not be independent of J, whereas these numbers are defined in terms of the Gromov-Witten invariant, so in particular, do not depend on the choice of the almost complex structure. So you cannot conclude from the theorem I just stated that these BPS numbers, the full finiteness part of the Gopakumar-Vafa conjecture. But nevertheless, you can use similar arguments to the one I just described with using this compactness and regularity for currents. And you can combine it with the proof of Ion and Parker to actually prove the full finiteness part of the Gopakumar-Vafa conjecture. So this is a new result with Eleni Ionel and Thomas Walpulski. And actually this proof, because it is modeled on the proof of the first part of the conjecture of Ionel and Parker, it actually proves at the same time both parts. So both parts, the integrality part and the finiteness part. But I don't want to talk more about this proof because maybe it's more related to the symplectic aspects of this theory. But instead, in the last few minutes, I want to mention some ideas on how to relate all of this to gauge theory. So what I'm going to talk about from now is not going to be mathematical results, but some ideas for the future. So I said that this naive count of curves is not an invariant because it will depend on J, because as you vary J, some pseudo-holomorphic curves can collapse to multiple covers. So you can ask, can I do something similar to what Taubes did in dimension 4 and equip these curves with weights in such a way that when J varies, the jump in weights compensates the jump in the number of curves, and correct this non-invariant to get an invariant. So in the simplest case, we have A equals to 2B, where B is a primitive class. And we might look for an invariant of the following form. First, you take sum over all embedded curves representing homology class A with some weights. If you put plus minus 1 here, that will be the naive count. But maybe you can come up with some other weights. And then you correct it with the count of curves in a homology class B, so A over 2, with some other weight. And crucially, I should allow these weights to depend on J. So you can ask, how should these weights depend on J? So in order for this number to be invariant, so you can consider a situation when you have a family of, so this is a family of J, so this is the arrow of time, and you imagine that you deform J from J0 to J1, and what can happen is that you can have a family of curves C twiddle T, which if this line that is a picture of the moduli space, this C twiddle of T disappears from the moduli space, say at time 1/2, because it collapsed to multiple cover. So as currents, it converges to 2 times C, where C is a curve in a homology class B. So that means that this sequence disappears from the moduli space of curves in the homology class A. So now if you compare this sum at the beginning, at the end of such a deformation, and you require the sum to be equal, the sum at time 0 to be equal to the sum at time 1, you get this formula that the weight, the W1 of C twiddle plus W2 of C should be W2 of C, but with respect to the final almost complex structure. So you really should see that these weights should depend on the almost complex structure. So the question is, how do you find weights which behave in this way? So for that, we need to understand when such a degeneration happens. And I already said that this happens exactly when there is a 2-value section of the normal bundle. So there are many ways you can look at this 2-value sections. You can either look at it as a section of N twisted by some orbifold local system, or a section of the second symmetric product of the normal bundle. So these two are equivalent points of view. In any case, we want this weight W2 to jump precisely when J is so that this section exists. And I said that these sections shouldn't exist for generic J because the corresponding operator has non-positive index. But if it has index 0, then for a generic family of J's, such a section might appear. So I want this weight to jump exactly when such a section appears. And this is related to a problem that was studied in G2 geometry, in the geometry of manifolds with special holonomy by Heides and Walpusky, following ideas of Donaldson, Thomas, and Siegel. So in that story, you want to count calibrated 3 manifolds inside 7-dimensional manifolds with special holonomy G2. And again, you don't expect a naive count of such submanifolds to be an invariant as you deform your G2 structure. So then you look for weights which will compensate for jumps in the number of such calibrated submanifolds. And Heides and Walpusky proposed that these 3 manifolds should be counted with weights given by the number of solutions to some non-abelian Seiberg-Witten equations. So now we can take the proposal and we can consider a dimensional reduction. So we can look at these generalized Seiberg-Witten equations over 3 manifolds of the form C times R, where C is a Riemann surface. And we can consider R invariant, translation invariant solutions, and we get some gauge theory equations on C. And that is our guess for what these weights should be. So let me write down these equations. So we want to define W2 by counting solutions to non-abelian vortex equation. And I wrote the general form of the equation. I didn't explain all the terms, but the point is that it's really something like a mixture of the vortex equation and the Hitchin equations. So there are some Delbar operators and some sections which are in the kernel of these operators. Then there is some algebraic condition and an equation involving the curvature. So this is something similar to what appears in the vortex equations, and this is a term similar to the one appearing in Hitchin's equations. And there are lots of sections here, so I don't want to explain everything, but the point is that Xi is a section of a normal bundle twisted by an endomorphous bundle of a rank 2 bundle, and A is a U2 connection. So these are gauge theoretic equations with structure group U2. And they're called the ADHM vortex equations because they're close related to the ADHM construction of instantons. And this is what you get from dimensional reduction of the equations studied by Heidis and Wolpuski. So why consider these particular equations? So this is related to the work of Taubes on compactness theory for generalized Seiberg-Witten equations. So now you can ask, let's say that we define W2 by counting solutions to these equations. And you see that this Delbar operator here is really a real Delbar operator, which is twisted by the germ of an almost complex structure. So this is something like something similar to the deformation operator of a J-holomorphic curve. So you can ask, how can it happen that the number of solutions to this equation changes? And this can happen when you lose compactness for the moduli spaces of solutions. And then following work of Taubes, we know that such change in the number of solutions can happen when some of the solutions escape to infinity. So when the L2 norm of this section Xi goes to infinity. So when this happens, so suppose the other variables stay bounded when this happens. So this equation is an equation for A, alpha, beta, and Xi, and suppose alpha, beta, and A stay bounded, and we can pass two limits. But the only bad thing that happens is that Xi goes to infinity. Then if you rescale everything by the L2 norm of Xi, essentially and you pass to the limit, essentially what you get is are these equations. You get the equation that Xi is J-holomorphic, but also satisfies these two equations. So let's see. Essentially, when you set everything equal to 0 here, right? So if you disregard all terms, that's what you get. And the idea is that because this goes to infinity, everything else is small. But now, if you remember, Xi was a section of a normal bundle times endomorphism bundle. That means that locally, over every point of the curve, we get two matrices, right? Because endomorphisms of V are represented by matrices, and moreover, these matrices commute, and they commute and they are normal. So if you have two matrices that commute and are normal, then you can simultaneously diagonalize them. And now the eigenvalues of these matrices will give you 2 points over C in the normal bundle. So this is the Hitchin spectral curve construction that essentially a data like this with psi being pseudo-holomorphic corresponds to a pseudo-holomorphic section of the second symmetric product of the normal bundle. So what I'm trying to say is that if you stare at these equations, then you see that the only way you can lose compactness is when you have one of these objects. And these are exactly the objects that caused the jump in the moduli space of pseudo-holomorphic embeddings. So you see that there is some relation between these two problems. So to summarize, here is a conjecture that for a generic J, we can define this weight by counting solutions to the ADHM vortex equation with structure group UK. Then you can define, so I considered the case when K was 2, but you can consider the general case. Now you can count, given a homology class, you can count curves in the homology class A over K for every K which is a divisor of A, equipped with this weight WK. And even though each of these individual sums is not independent of J, the conjecture is that if you sum over everything, you get something that does not depend on J, and therefore is a symplectic invariant of X. And there's a third part of the conjecture, that this recovers the Pandari-Pandey-Thomas invariance in algebraic geometry, which I didn't talk about, but these are defined using sheaf theory. So this is the proposal. And I have some comments. Right, to prove that these ways are well defined and to study how they change when I change J, you have to study the compactness problem for these equations. And there's a lot of work by Taubes, Heidis, Valpusky, Zhang on this. So actually these authors worked on the three-dimensional equations, which are much more complicated. So the hope is that once you reduce it to Riemann surfaces, everything becomes easier. I will not talk about this, but now to prove, now even if you can define these weights, to prove that this sum actually is independent of J, you have to combine the theory for the gauge theoretic equations with the theory for pseudo-holomorphic curves and show that all the jumps cancel each other out. So you have to combine the theory for these vortex equations with the compactness and deformation theory for curves. And this is related to this problem of multiple covers. And I expect that similar methods of geometric measure theory to the ones I mentioned earlier will play a role in this discussion. So thank you for your attention. And that's all.
Are there any questions?
Do these vortex equations have an algebraic geometric interpretation in the algebraic case?
Yes. Let's see. Yeah. So I mean, as you explained in your work with Siegel, the point is that you have C and a normal bundle, and right, essentially every point of the normal bundle you will have at every fiber bundle you will have not an instanton, but what do I want to say? And you are doing the on every fiber, normal fiber, you are doing the ADHM construction. So you have a sheaf over you have a sheaf over every normal fiber.
Another question was, in some situations you have a problem from the reducible solutions of these generalized Seiberg-Witten equations, but that doesn't happen here, presumably?
Yes, I think when genus is greater maybe than 1, you can put some homologically non-trivial perturbations here on this side and this side to rule out reducibles. But I don't know, when G is equal to 0, I think there might be some problems.
Does the problem of first Betti number being equal to 0 or 1 also appear here too when you get to the Seiberg-Witten weights?
Well, if you look at it from the 7-dimensional point of view, if you have a Calabi-Yau times S1, then all the 3 manifolds you consider are C times S1.
Oh yeah, I see.
B1 is always at least 1.
Oh, so you can get a numerical theory. I see.
Is there some geometric interpretation of the limiting system when you rescale everything?
Mhm.
Can you talk about this a little bit?
Yes, so if you look at solutions to, A, Xi, so A and Xi that satisfy this limiting system are corresponds to sections of the second symmetric product. But then there were also these alpha and beta. So these have an interpretation of if a section of the symmetric product gives you also a double cover. Just the graph of that is a double cover, branch double cover, and alpha and beta then correspond to solutions of the vortex equations on C twiddle. So it's essentially a divisor on C twiddle. So this pair gives you essentially a branch cover, and alpha and beta gives you a divisor on C twiddle.
Alexander, if you, rather than taking the, so you can get a homological invariant too, or, oh no, because this 4-dimensional submanifold, there is no homological version, right?
To get a homological invariant, you would so you would have to have some sort of Floer theory in 1 dimension higher. So
yeah,
you would want now if you have 2 symplectic 6 manifolds, you would want to find a differential. You would want to have a chain complex which is generated by pseudo-holomorphic curves and solutions to the vortex equations, and the differential would count solutions to the associatives in this
C times S1. Yeah.
R times your symplectic manifold, and then solutions to the 3-dimensional Seiberg-Witten equations on these associatives.
And then you can think about that maybe in your line of work as categorification of PT invariants.
Yes.
I see.